In 1989, astronomers discovered a huge structure called the Great Wall, located 200 million light-years away from the Milky Way. Stretching 500 million light-years in length, it became a megastructure consisting of filamentous clusters of galaxies, first discovered by humans in the vast expanses of the universe. As time passed, technology advanced, providing new opportunities for observations at the dawn of the 21st century. In 2003, astronomers announced the discovery of the Great Wall, which is located over 1 billion light-years away and stretches 1.37 billion light-years in length. For a while, the Sloan Great Wall became the sole leader in the ranking of the largest structures in the universe, until in 2012, a huge group of quasars occupying an area of 4 billion light-years was discovered. However, the group of quasars held the top spot for only a short time, and in 2013, the Hercules Corona Borealis Great Wall pushed it off the top spot. The structure was discovered by correlating gamma-ray bursts. These are very bright explosions from distant massive stars, the most powerful flashes in the universe. A typical burst releases more energy in less than 1/10 of a second than the sun does in its entire lifetime. Gamma-ray bursts are very rare in a typical galaxy, occurring only once every few million years. The stars that cause these explosions are very massive, so the material necessary for their formation must be present in large quantities. Therefore, these bursts can be used to track whether there is a galaxy in that direction or something larger, such as a structure. So, up until 2012, astronomers collected such bursts in the sky and created a map on which they noticed something interesting. 19 gamma-ray bursts had very similar and closely spaced redshifts, indicating a very large group of galaxies and matter in a megastructure located approximately 10 billion light-years away from us in the constellations of Hercules and Corona Borealis. This is what gave it its name, the Great Wall, although it is much larger than both of these constellations combined. The structure also covers the constellations of Vulpecula and Gemini, and in addition, the wall has a more circular shape than a long one. For some reason, it was named and picked up by the media as the Great Wall of Hercules and Corona Borealis, despite being much larger than those two constellations. Hercules' northern crown, the length of this truly great wall is about 10 billion light-years. We are often asked to speak about distances in kilometers, supposedly it is easier to understand. But guys, it's like calculating the distance from Vladivostok to Sydney in millimeters. Although in our case, the number will be even bigger. But I want to remind you that it might be easier for someone to imagine the Milky Way. For those who don't know, the galaxy we live in is only 100,000 light-years in diameter, and the distance from the Milky Way to the Andromeda Galaxy, which will eventually collide with us, is only 2.5 million light-years. Here, however, we are talking about 10 billion, which is truly impressive. And now let's add to this the width of the structure. It is 7.2 billion light-years, and the thickness is almost 1 billion light-years. We end up with truly indecent sizes that are frightening to imagine. The Great Wall of Hercules' northern crown occupies 10% of the area of the entire observable universe. The structure contains billions of galaxies that are connected to each other by gravity. But what is amazing, as you may have noticed, is that it is 10 billion years old, which means that the structure existed less than 4 billion years after the Big Bang. This is where the confusion begins in the scientific community. But first, let's take a closer look at what this redshift is. I think it will be interesting to learn about it or useful to refresh your memory for those who already know. It is also very important to us, but more on that later. So, there is a certain Doppler effect that you have probably heard of. Its essence is quite simple. If a source emitting a wave is approaching an observer, the latter sees a decrease in the wavelength. If, on the contrary, the source moves away from the observed wavelength increases. If, on the contrary, the source moves away from the observed wavelength increases. In other words, if a light source, such as a star, is moving away from an observer on Earth, the wavelength of the light waves from the source will increase and the light will appear red to the observer. Conversely, if the star is approaching the Earth, the light waves will be compressed and the light will appear blue. However, since blue and white stars are the brightest, the human eye perceives their color as white. This Doppler effect applies not only to light waves, but also to sound and other wave oscillations. Observing this effect in the universe, where there are many stars, is much more interesting. Doppler himself believed in this opinion, and in 1842 he published a paper on the color of light from binary stars and some other stars in the sky. Later, in 1848, the French physicist Hippolyte Fizeau first pointed out the shift in the lines in star spectra and proposed to explain this phenomenon using the Doppler effect. The greater the redshift in the object's spectrogram, the faster the object is moving away from us. By the way, rotation of galaxies was discovered thanks to the redshift of light from galaxies moving away from us. Distant galaxies have greater redshifts than nearby ones, and the magnitude of this shift increases proportionally to the distance. Therefore, the farther the galaxy, the faster it is moving away from us. The redshift is also caused by the expanding space and the intrinsic motion of galaxies. This is all explained simply by the fact that during the time it takes for light to travel through space from a source to us, space is expanding. During a twofold expansion of space, the wavelength of light will also double. This is all relatively simple, although one could delve deeper into the subject, which is quite extensive. However, what awaits us is the Great Wall of Hercules Corona Borealis. What is wrong with it is that its structure contradicts the theory known as the cosmological principle. This principle tells us that the universe is roughly homogeneous, meaning that random deviations in the structure and mass of matter between different objects in the universe should be very insignificant. Homogeneity should be evident on a scale of 250 to 300 million light-years, also known as the end of greatness. The maximum size of any structure should be about 1.2 billion light-years, based on the aforementioned value, and no structure should be larger than this size. I assume that matter is distributed equally from the Big Bang. However, the Great Wall, which is 8 times larger than this limit, calls into question the entire cosmological principle. As a result of this discovery, it was named so large that it should not exist. Furthermore, the structure is located 10 billion light-years away from us, which means we see it as it was 10 billion years ago. This implies that it formed just 3.8 billion years after the Big Bang, which is too short of a time frame for the formation of a gigantic wall 10 billion light-years long. In other words, the northern Corona Borealis Hercules violates the model of the universe's evolution, which does not allow for the formation of such complex and massive structures at this point in time. Even Istvan Horvath, a researcher of the structure of concepts, has no idea how it was formed. During this time, the discovery implies that the universe is older than we thought, which greatly undermines the theory of the Big Bang, which is already being tossed back and forth like a boat on waves in a calm ocean during a storm. Could the discovery of such a huge structure be completely erroneous? It is highly doubtful, but to some extent hypothetical. There are astronomers who question the theory of redshift. The idea was put forth that light reddens due to its extremely long journey through the sparse gas of intergalactic space, resulting in a loss of short wavelength spectra and nebulae becoming redder, although spectral lines do not shift. But we remember that redshift precisely implies this process. Perhaps light loses some of its energy from infinite travel through the universe, which leads to an elongation of the waves that generate redshift. However, this idea has not been proven yet. No one has been able to show that light can lose energy in any way, and where this energy goes is also a big question. For example, in the case of quasars, it is evident that the further away they are from us, the more redshift they have. By the way, despite all this, there is such a concept as statistical significance. For the phenomenon of the Great Wall of Hercules and the Northern Crown is very scarce, even on English language resources, but we have gathered the most interesting information for you. So please, guys, don't hesitate to like and comment. We need your support. Until our next interesting meeting. Our planet is a part of the solar system and is located in one of the spiral arms of the Milky Way galaxy, which has a diameter of 100,000 light-years and contains about 400 billion stars. This is truly an enormous number that is difficult to even imagine, but there is also the Andromeda Galaxy, which is at least 2.5 times larger than our Milky Way. Andromeda, as well as several dozen other galaxies, is a part of the local group and is the largest in this cluster. Compared to it, the Milky Way doesn't seem so huge. Today we will tell you about the largest galaxy in the observable universe, the size of which is so enormous that it is impossible to imagine using the Yerkes classification system. The abbreviation CD is reserved for the largest galaxies, and the lowercase letter c indicates that the galaxy is a supergiant, while the uppercase letter D indicates that it is surrounded by a halo of scattered light. All galaxies have an enormous width of up to millions of light years, which greatly exceeds the effective radius, that is, the radius of the brighter inner region from which 50% of the galaxy's light is emitted. Such objects are usually central galaxies in some cluster consisting of hundreds or even thousands of galaxies. Therefore, astronomers often use this abbreviation, redefining its original meaning as an abbreviation for the central dominant galaxy. However, since compact disks are also the brightest in the cluster to which they belong, CD is also mentioned with the abbreviation BCG, which denotes the brightest galaxy in a given cluster. Such galaxies are the true monsters of the universe. They are formed, according to the theory, by sequential mergers with smaller galaxies. Over time, thanks to the material of the latter, they become more massive and inevitably fall into the center of their cluster. In fact, gravitational friction with other galaxies allows compact disks to acquire an immeasurable amount of mass. In other words, galaxies sit for billions of years and turn into giant deposits of stars and gas, primarily with an elliptical shape. They are usually populated with old stars and have low surface brightness, and their halo is so large that astronomers find it difficult to determine where the galaxy ends and intergalactic material begins. By the way, we have a separate video on what types of galaxies exist and how they appear. Despite being self-critical, this video turned out quite well, so for those who haven't seen it and are interested, there's a link in the upper right corner. Don't forget to rate it. Only one representative of the S0 galaxy classification exists in the large galaxy cluster Abell 2029, located on the edge of the constellation Virgo, and that is the OISI 1101 galaxy. The abbreviation OISI stands for the Catalogue of Nebulae and Star Clusters, published by John Dreyer in 1895, and 1101 is the number assigned to this object in the catalogue. At first, it was thought to be a nebula, but in the 20th century, it was found to be a galaxy, and its redshift indicates that it is located at a tremendous distance from Earth, just over 1 billion light-years away. Practically everything we know about OISI 1101 today is based on a 30-year-old study whose results were published in October 1990. Observations were made on a 90-centimeter telescope at the Kitt Peak National Observatory, with a digital camera attached to the telescope's focus that had a resolution of 512 by 300 pixels. This is much lower than the current cheapest smartphones, but this did not prevent the telescope from performing well. Astronomers obtained 16 partially overlapping images of Abell 2029, combined into a kind of cross with 9 frames oriented in the east-west direction and 7 frames oriented in the north-south direction. The overall image covered an area of 34 by 21 arc minutes and was concentrated on the dominant elliptical supergiant galaxy IC 1101 and its cluster. IC 1101 is a very unusual galaxy, with the emitted light weakening from the center outward and almost entirely conforming to the profile of an elliptical galaxy. The halo of the galaxy could be distinguished up to the maximum distance at which the light emitted by the cluster could be separated from the scattered light of the sky, which is approximately 1.2 megaparsecs from the center of Abell 2029. In simpler terms, the diameter of IC 1101 is about 6 million light-years, which is almost 60 times larger than the diameter of the Milky Way and 2,000 times more massive. The energy emitted from IC 1101 is equivalent to at least 1 trillion suns and accounts for more than a quarter of all the light emitted by Abell 2029, a cluster that, as a reminder, includes thousands of other galaxies, hundreds of which are also not small. If IC 1101 were located in the Milky Way, it would have swallowed up our nearest neighbors, the large Andromeda and Triangulum galaxies, which are located at distances of 2.5 and 2.7 million light-years from us, respectively, as well as smaller galaxies such as the Large and Small Magellanic Clouds, which are located in the IC 1101 galaxy. If we were to look up at the night sky, we would see thousands of times more stars, visible more or less evenly in all directions than we do now, but this is a unique phenomenon. According to scientists' calculations, the ratio between mass and light in April 2029 is far from balanced. To understand how scientists arrived at this conclusion about the presence of dark matter, we need to examine the relationship between mass and light in the galaxy or cluster of galaxies. We will use the mass and luminosity of the Sun as our units of measurement. If the galaxy were composed entirely of stars identical to our own, its mass-to-light ratio would obviously be 1. However, the galaxy is made up of many different types of stars, giants, supergiants, and these stars have an unbalanced mass-to-light ratio in favor of the latter. In a very ancient elliptical galaxy where there is no recent star formation activity, such as IC 1101, other types of objects dominate, mostly main sequence M-type stars, or so-called red dwarfs, and white dwarfs. However, the mass-to-light ratio calculated for IC 1101 is so unbalanced in favor of mass that it cannot be associated with any likely type of stellar population within a radius of 20 kiloparsecs from the center. This ratio is approximately 12 solar masses per observed solar luminosity. As one moves away from the center, the ratio rapidly increases. At a distance of approximately 200 kiloparsecs from the center, it exceeds 100 solar masses per solar luminosity, and at distances greater than 1 megaparsec, the ratio increases to thousands of solar masses per solar luminosity. Such a large amount of matter that cannot be observed or associated with any stellar population forces astronomers to fill the gap with mysterious concepts of dark matter, which is a substance that does not emit light and manifests its effects solely through gravity. IC 1101 seems to be filled with dark matter, and in addition to that, at the center of IC 1101, there is an astronomical radio source with a code name that emits two jets in opposite directions. This means that in the center of this huge galaxy, there is a supermassive black hole, which is confirmed by research published in the monthly notices of the Royal Astronomical Society in October 2017. The authors of the study analyzed the core of IC 1101 photometrically and found that it is not only enormous, bigger than any other known galaxy, but its brightness is significantly lower than expected. This deficit of light is likely a consequence of a long series of galactic mergers during which double systems of supermassive black holes gradually merged in the center of IC 1101. According to calculations, such a truly supermassive black hole that emerged as a result of the merger of all black holes could have a mass of 40 to 100 billion solar masses. If these calculations are correct, Earth has not observed the most supermassive black hole in the universe, since, as we already know, old stars predominate in the IC 1101 axis, and new ones are not born as frequently as in the Milky Way. It is considered a dying galaxy surviving by absorbing its closest neighbors. We know that this dying galaxy emits a blue color due to its fullness of young stars, while the yellow galaxy, such as IC 1101, is gradually dying. Lastly, I would like to remind you to subscribe to the channel because it is interesting as we have even more cool videos about space ahead, and also don't forget to like this video. There are very few likes. Are you being greedy? You don't need to be greedy, just give it a like and hit the bell icon. There are several ways for the formation of black holes, from the collapse of a supernova core to the merging of neutron stars with the collapse of a massive amount of matter. There are black holes of the lower limit that can have 2.5 to 3 solar masses, and there are supermassive black holes whose mass exceeds 10 billion solar masses. These are the upper limits of black holes, and they are usually found at the centers of galaxies. Those who are interested in or studying these cosmic spheres have many questions. For example, how stable can black holes be? Which type of black hole will exhaust its energy first, a large supermassive one, or a small one of the lower limit? Is there a critical size for the stability of a black hole? We have found suitable material for you to think about. Let's talk about a black hole with a mass of 10 to the power of 12 kilograms. It can be stable for several billion years, while a black hole in the mass range of 10 to the power of 5 can explode in a second, and it certainly cannot be called stable. The key is to find the so-called golden mean, where the inflow of matter is balanced by Hawking radiation. The first thing to consider is the stability of the black hole itself. Any other object in the universe, whether it is physical or otherwise, has forces holding it together against the universe that tries to tear it apart. A hydrogen atom is a sturdy structure that can be destroyed by only one ultraviolet photon. To ionize an electron and destroy the atomic nucleus, a higher energy particle like a cosmic ray, accelerated proton, or gamma ray is needed. Energy particles like cosmic rays, accelerated protons, or gamma rays are found in large structures such as planets, stars, or even galaxies. The gravitational forces that hold these colossal structures together are immensely strong. Typically, to break apart such megastructures, either a thermonuclear reaction or an incredibly strong external gravitational force is required, for example from a passing star, black hole, or galaxy. However, in the case of black holes, things are very different. The mass of a black hole, instead of being distributed throughout its volume, is compressed into a singularity. For a non-rotating black hole, this singularity is a zero-dimensional point, while for a rotating black hole, it is a much better described infinitely thin one-dimensional ring. Additionally, all the contents of mass and energy within a black hole are contained within its event horizon. Black holes are the only objects in the universe with an event horizon, beyond which it is impossible to return once crossed, as no acceleration or force can extract matter, mass, or energy from within it. This means that black holes, once formed by any means possible, can only grow and will never be destroyed. They grow relentlessly and continuously. We observe all kinds of phenomena in the universe, such as quasars, blazars, active galactic nuclei, microquasars, stars that do not emit any light, X-ray, and radio bursts from galactic centers, but all of them lead us to black holes, determining their masses. We try to learn about the physical sizes of their event horizons, and anything that collides with, crosses, or even grazes the event horizon will inevitably fall inside and then, due to the conservation of energy, increase the black hole's mass. This process occurs with every black hole. Known materials from other stars, interstellar dust, gas clouds, even radiation and neutrinos left over from the Big Bang, all get pulled in. Any matter that collides with a black hole increases its mass. The growth rate of black holes depends on the density of matter and energy surrounding them. The monster at the center of our Milky Way is growing at a rate of 1 solar mass every 3,000 years. For example, the black hole at the center of the Sombrero Galaxy is growing even faster, at a rate of 1 solar mass every 20 years. Generally, the bigger and heavier the black hole, the faster it grows, depending on the matter it encounters. Over time, the growth rate slows down. However, since the universe is only about 13.8 billion years old, black holes continue to grow at an impressive rate. On the other hand, black holes don't just grow over time. There is also a process called Hawking radiation, which is associated with the fact that space is highly curved near the event horizon, but becomes flat as you move away. If you are at a great distance, you can see slight radiation emitted from the curved region near the event horizon. This is related to the fact that the quantum vacuum has different properties in different curved regions of space. The end result is that black holes emit thermal radiation in the form of photons in all directions around them, filling a volume of space that is primarily enclosed within 10 Schwarzschild radii of the black hole's location. It may seem strange, but the smaller the black hole, the faster it evaporates through Hawking radiation. This is an incredibly slow process, however. A black hole with the mass of our Sun would take 10 to the power of 64 years to evaporate, while the black hole at the center of our Milky Way will last for 10 to the 87th power years. The most massive black holes in the universe will last for 10 to the 100th power years. A black hole with the mass of the Earth will live for 10 to the 47th power years, while a black hole with the mass of the Great Pyramid of Giza, 6 million tons, will last for about 1,000 years. A black hole with the mass of the Empire State Building will last for about a month, and a black hole with the mass of a typical human will peak in size and then evaporate in a fraction of a second. As far as we know, the universe can contain black holes of unimaginably different sizes. If the universe were filled with lightweight black holes weighing up to 1 billion tons, they would have all evaporated by today. There is currently no data on the existence of black holes with masses between these lightweight black holes and those born from the merger of neutron stars. In theory, such black holes could have a mass of 2.5 times that of the Sun. X-ray observations indicate the existence of black holes in the range of 10 to 20 solar masses. The LIGO observatories have shown the existence of black holes with masses ranging from 8 to 62 solar masses, and of course, supermassive black holes are found everywhere in the universe. Today, all existing black holes are gaining matter faster than they are losing it due to Hawking radiation. A black hole with the mass of the Sun loses about 10 to the 28th power joules of energy every second due to Hawking radiation, but even a single relic photon from the Big Bang carries 1,000,000 times more energy than this. There are about 411 such photons per cubic centimeter of space, and they move at the speed of light, colliding 10 trillion times per second in each cubic centimeter. Thus, even an isolated black hole in the depths of intergalactic space will have to wait until the universe matures to 10 to the 20th power years, 1 billion times its current age, before the rate of black hole growth falls below the rate of Hawking radiation. Let's assume you live in intergalactic space, far away from normal matter and dark matter, away from all cosmic radiation, starlight, and neutrinos, and you only have photons remaining from the Big Bang. How big should your black hole be so that the rate of Hawking radiation emission and photon absorption in your black hole is balanced? The answer is around 10 to the power of 23 kilograms, which is approximately the mass of the planet Mercury if it were a black hole. It would be about 1 millimeter in diameter and would emit radiation at a rate of about 100 trillion times faster than a black hole with the mass of the Sun. In our universe, a black hole with this mass would absorb as much microwave radiation as it loses in Hawking radiation. But this was just an example, and if you need a realistic black hole, you cannot isolate it from the remaining matter in the universe. Even if black holes are ejected from galaxies, they still pass through the intergalactic medium, colliding with cosmic rays, starlight, neutrinos, dark matter, and various massive and massless particles. It is impossible to avoid the cosmic microwave background no matter where you go. Black holes constantly absorb matter and energy and grow in mass and size, and they also emit energy. However, for all the black holes that exist in our universe to begin to exhaust themselves faster than they grow, it will take about 100 quintillion years, and the evaporation time will be even longer. Well, it seems like black holes will outlast everything and everyone. Humanity is striving to learn about the universe, explore it, and conquer it, but at the same time, almost everything here is shrouded in mystery and unknown. However, it cannot be said that everything is hopeless because the level of technology and our knowledge is growing. It may not be as rapid as many would like, but progress exists. For example, we already know for sure that stars and galaxies are located in expanding space, not randomly. Despite the chaos, the universe is not a random mess of objects. It may seem amazing, but the universe has a structure consisting of massive threads of galaxies. All these thin threads are real galaxies. This is the cosmic web, as scientists called it. Galaxies are part of clusters, which, in turn, form larger structures that are gravitationally linked to each other. The dark voids between them are cosmic voids, or as they are called in warps, and they are actually of giant sizes. The structures of galaxies also excite the imagination with their sizes, which is why they are also called walls. The largest such structure discovered to date is the Great Wall of Hercules Corona Borealis, which is 10 billion light-years long and contains several billion galaxies. There are also smaller walls that have been discovered since the last century, with different sizes, but they all have one common feature: they are very far from us. The Hercules Corona Borealis wall is located approximately 10 billion light-years away from Earth. Interestingly, scientists were so closely examining distant objects in the universe that they missed one of these walls that was right under their noses. In 2020, astronomers discovered that there is a huge wall consisting of thousands of galaxies beyond the Milky Way. There exists a massive wall consisting of thousands of clusters of trillions of stars, exoplanets, dust, and gas arranged in the shape of a curtain. This wall is unique because its distance is only an average of 500 million light-years away. It is the most massive structure we have ever seen, so close that it stretches beyond the dust, gas, and stars of our own galaxy, from the constellation Perseus in the northern hemisphere to the constellation Phoenix in the southern hemisphere. This wall is so massive that it affects the local expansion of the universe. Astronomers called it the Southern Pole Wall, a colossal structure spanning an unimaginable diameter of 1.37 billion light-years. As some parts of this wall are still hidden from us, this structure could possibly be even larger. Astronomers have promised to find out more about it soon. But why has no one seen one of the largest threads of galaxies in the universe right on our doorstep? It's all due to the zone of avoidance, which is not a scary thing nor an alien dome that separates us from the cosmos, but rather an area of the sky blocked by our own galaxy, making it difficult to observe cosmic objects from Earth. The interstellar light attenuation by stars in the plane of the Milky Way obstructs observations in the visible part of the spectrum for about 20% of the sky behind the galaxy. Therefore, catalogs compiled from observations in the visible spectrum are usually incomplete near the galactic plane. This obstruction is the only way to bypass it is to use X-rays and infrared light, although these methods do not produce the clearest images. By the way, those 20% of the universe blocked by the zone of avoidance turned out to be where the famous Great Wall is located, hidden by gas and dust clouds and stars. If you still don't know what the Great Attractor is, it was discovered by astronomers in 1986. They found that galaxies in a huge strip of the sky towards the constellation Centaurus are flying away much faster than predicted by Hubble's law, as if something is attracting them. This something is called the Great Attractor. Now, let's get back to the newly discovered Southern Pole Wall. How was it possible to detect it if the zone of avoidance makes observation so difficult? First, the team of researchers used a database that contains distance calculations for nearly 18,000 galaxies. These distances are calculated using redshift, which measures how fast an object is moving based on the degree to which its light waves are stretched. Another group of researchers used this database to calculate another parameter known as peculiar velocity, which represents the velocity of a galaxy relative to its motion due to the expansion of the universe. Using these two parameters, the team could calculate the motion of galaxies relative to each other, and these motions revealed the gravitational influence of a huge mass. With algorithms, the team used these motions to map the three-dimensional distribution of material in the Southern Pole Wall, even beyond the zone of avoidance. The densest part of the wall lies above the South Pole, then it turns north and is within 300 million light-years of our galaxy. Galaxies move along a curved arm towards the cluster at the South Pole, and from there they go to another giant structure, the Shapley supercluster, 650 million light-years away from us. The Southern Pole Wall connects many other cosmographic features, such as the distribution or absence of galaxies. Researchers recently discovered in the expanding universe, according to Hubble's law, the farther a galaxy is, the faster it is moving away from us. This movement causes light from galaxies to shift towards longer, more red wavelengths and lower frequencies, like the wail of a receding ambulance. By measuring the distance between galaxies, researchers were able to distinguish movement caused by cosmic expansion from movement caused by gravitational unevenness. As a result, astronomers discovered that galaxies between Earth and the South Pole Wall are moving away from us slightly faster than they should be, while galaxies behind the wall are moving slower than they should be due to gravitational resistance. One can marvel at how such a large and relatively nearby structure remained unnoticed all these years, but in the expanding universe, there is always something to look at, and we will undoubtedly tell you about the most interesting things. For you, it's a trifle, But for us, it's an assessment of our work and inspiration for future episodes. Recently, in one of our videos, we talked about IC 1101, the largest galaxy in the visible universe, with a diameter of 6 million light-years, which is nearly 60 times larger than the Milky Way's diameter. If you imagine that it is in the place of our galaxy, Andromeda, the Triangle Galaxy, and the large and small Magellanic Clouds, in addition to all of them, would be engulfed by this giant. Without a doubt, among galaxies, IC 1101 is a true monster, but its size simply pales in comparison to another class of objects, radio galaxies. Radio galaxies are very rare objects in the universe, colossal in size, with supermassive black holes at their centers that actively consume gas and dust from the surrounding environment. This activity initiates the launch of high-energy jet streams capable of accelerating charged particles around the supermassive black hole to almost the speed of light. These jets are very clearly observed in radio waves, and in most cases, they have a length of 1,000 light-years or more, and differ from ordinary galaxies in that they have much greater radio emission, which often exceeds their optical and luminosity. Meet J1420-0.545, currently the largest known representative of radio galaxies. It is located on the border of the constellations Draco and Ursa Minor, and is approximately 2.3 billion light-years away from Earth. It has the largest radio structure ever observed, which takes the form of spheres or cocoons formed by shock plasma and streams expanding outward into the intergalactic medium. To say that this radio galaxy is huge is an understatement. Its length is 4.69 megaparsecs, or about 16 million light-years, and its mass is estimated to be at least 185 trillion solar masses, almost 3 times larger than the aforementioned IC 1101. The information about this object is very limited, but much more is known about it than any other radio galaxy. However, some information has been gathered. J1420-0.545 was discovered in 2008 as 2 radio lobes located 17.4 inches apart. Further observations made with the Giant Meter Wave Radio Telescope confirmed the presence of a core midway between them and corresponded to a previously known faint galaxy. Redshift values were available, but with significant uncertainties. Therefore, in 2015, optical photometry was performed at the Mount Suora Observatory, and the obtained data proved to be useful. Spectroscopy helped determine which galaxy the astronomers were looking at. Unlike the radio lobes, no optical emission from the center was visible, and it was impossible to image the galaxy as we would, for example, take a picture of our neighbor Andromeda. J1420-0.545 is an elliptical galaxy, which typically forms over time through the merger and collision of small galaxies of different types. The level of star formation is low, meaning there are relatively few young, hot, blue stars compared to spiral or lens-shaped galaxies. Currently, at some wavelengths, a decrease in radiation is observed due to the absorption of metals in the star's atmospheres in most galaxies. Hot stars fill this gap if it is present, but there are very few in elliptical galaxies. So how did it become such a large radio galaxy? This size is not unprecedented. The giant object Cygnus A was previously discovered, and it has a diameter of about 15 million light-years, or 4.4 megaparsecs, and its age is approximately 110 million years. However, what is surprising is that the age of J1420-0545 is only 47 million years. So why is such a relatively young radio galaxy so large? The answer turned out to be the intergalactic medium, a hot plasma filling the space between galaxies. The density of matter at its center is lower than in the center of TREES 236 by about 20 times. The gas pressure opposing expansion in jets is also significantly lower, and the power of the galactic core in J1420-0545 is 50% higher than in the comparable TREES 236. This, combined with the significantly lower density of matter in the surrounding environment, meant that J1420-0545 experienced much less resistance as it traveled through intergalactic space and could therefore expand faster and farther in a shorter time. The question arises, why is the local matter so rarefied on such a large scale? Initially, the group of scientists believed that this was simply a natural area of space similar to a void, a low density within a dozen megaparsecs formed shortly after the Big Bang. However, after additional measurements, they considered an alternative version that J1420-0545 was the result of the growth of activity in the galactic core. The team of astronomers suggested classifying J1420-0545 as a double radio galaxy, as it has two pairs of petals that are aligned to within a few degrees, indicating that the central active galactic core had a period of activity, then turned off, and then restarted. Moreover, the jets are narrow, which is characteristic of double radio galaxies undergoing their second period of activity. If this hypothesis is correct, then there should be a second weak core after the first period of activity. The shell should have cooled rapidly due to energy losses from synchrotron radiation, but what about the question we posed in the title? Does J1420-0.545 deserve the title of the largest known galaxy? It is still unknown how large its stellar halo is, but it is undoubtedly much smaller than the giant spherical shell that surrounds it. At the same time, this shell represents a very clear boundary between the galaxy and the intergalactic medium, and the shocked plasma inside it should behave quite differently from the plasma in the intergalactic medium. Ironically, unlike ordinary elliptical galaxies that have scattered halos, we can pinpoint where this giant ends and where intergalactic space begins. Perhaps one day we will discover and study another giant radio galaxy even larger than J1420-0.545, and do it so well that it will answer all questions. However, for now, this question should remain open, and all we need to do is wait and see. In 2003, astronomers discovered a dwarf planet in the Kuiper Belt called Sedna. At that time, it was the most distant object in the solar system. The discovery of Sedna was revolutionary, including its role in Pluto losing its status as the ninth planet. It was thanks to Sedna that scientists finally understood that the Kuiper Belt is a true treasure trove for astronomers. Most importantly, the discovery rekindled discussions about the existence of Planet 9, which scientists had been unsuccessfully searching for since the 19th century. There is a massive object located on the outskirts of the solar system that is causing some changes. There is every reason to believe that on the outskirts of the solar system there is a massive object that, by altering the trajectories of smaller celestial bodies, causes their orbits to deviate from their original course, clearly under the influence of some gravitational source. Oval orbits are always directed in one direction and deviate by the same degree. Today, scientists Michael Brown and Konstantin Batygin are practically certain that this is the ninth planet and seem ready to dedicate their entire career to this discovery. However, not all scientists agree that this is indeed a planet. Some suggest that these gravitational distortions are caused by a black hole, not the massive black hole formed by the gravitational collapse of a star, but a very small, compact black hole the size of a bowling ball or even a ball. Such objects may be scattered throughout the universe and are called primary black holes. The existence of primary black holes was first hypothesized by Soviet scientists Yakov Zeldovich and Igor Novikov in the late 1960s. Their idea was based on the Big Bang model, which takes us back 13.7 billion years to a time when the universe was still very young and incredibly hot and dense, a point of unimaginable temperature and instability. Later in the development process, a very important event occurred. The force of gravity separated from the other three fundamental forces, the electromagnetic, weak nuclear, and strong nuclear forces. This period in the life of our universe lasted only 1/6 of a second and is called the Planck epoch. At the end of this period, the universe was still microscopic, with only 1 Planck length in diameter, but it already contained all the ingredients necessary to create the universe as we see it today. There were fluctuations in density and non-uniform conditions that could have caused gravitational collapse in the densest areas, forming primary black holes. The hypothesis of Zeldovich and Novikov was first picked up and deeply studied by Stephen Hawking. In 1971, he calculated that such black holes could have a mass similar to that of small asteroids, and today there are already 3 ranges in which the existence of primary black holes is possible. The first corresponds to the mass of small asteroids, the second to the mass of planets, and the third to masses in the range of several solar masses. However, since primary black holes were not formed as a result of star collapse, they can be of any size. Class 1 primary black holes are probably already impossible to see, as the smaller their mass, the stronger their radiation and the faster they lose mass. This process is called Hawking radiation, and it obviously accelerates itself and ends in a flash, but no such flashes have been observed yet. Moreover, such objects are not massive enough to actively absorb matter and form a bright accretion disk, which further complicates the detection process. Primary black holes in ranges 2 and 3 differ from black holes formed as a result of star collapse only in that they do not initially rotate. Therefore, they can be detected, for example, by observing gravitational lensing, the distortion of the path of light rays in the gravitational field of massive objects. Stephen Hawking suggested that there should be enough primary black holes in the vicinity of our Milky Way, and if so, considering that many primary black holes were formed in the early stages of the Big Bang, they should exist today, and we should be able to observe them. However, no one has yet been able to boast of such observations, and primary black holes exist only hypothetically. However, if they are indeed real, they will help solve many important cosmological problems, in particular the problems of dark matter. In 1994, 3 Russian astrophysicists, Pavel Ivanov, Pavel Nazelsky, and Igor Novikov, presented works estimating the number of primary black holes with a mass of about 1 to 10 solar masses. The scientists pointed out that under certain conditions, enough of these objects could have formed to explain the effect that is usually attributed to dark matter. Primary black holes can contribute significantly to the invisible mass of the universe. According to current estimates, dark matter accounts for about 25% of the unaccounted mass of the cosmos. A primary black hole is therefore an excellent candidate for the role of dark matter. In addition, primary black holes are also attributed to the mergers of pairs of black holes, which is not easy to imagine how such pairs could arise. The problem is that if they formed from massive stars, all models of the evolution of massive star pairs indicate that one should become a black hole faster than the other and then steal material from the second star by pulling matter from its outer layers. After this, the second star is not expected to become a black hole. One hypothesis is that they are just primary black holes of moderate mass that were never stars. Another hypothesis is that they are supermassive black holes in the centers of galaxies, meaning that black holes allowed galaxies to form rather than the other way around. Quasars are already known today, objects in the centers of which are supermassive black holes with redshifts corresponding to events that are 12.9 billion years old or less. What is particularly surprising is the mass of black holes in the centers of such quasars, which is hundreds of times higher than that of Sagittarius A*, the supermassive black hole with a star in its center. However, our galaxy is old enough that 12.9 billion years ago, when the universe was not even a billion years old, these dozens of black holes couldn't have accumulated such enormous mass. The accretion disk through which a black hole captures matter allows it to grow no faster than millions of solar masses per billion years. Similar problems are observed in other galaxies, even the youngest of which formed 400 million years after the Big Bang, during which time it was theoretically impossible to form a sufficient number of stars. This suggests that primary black holes are like seeds of the Big Bang that were supposed to accelerate the evolution of galaxies by attracting matter from surrounding space with their gravity. While there are many ways to detect primary black holes and dispel doubts about their existence, only a few can currently be applied in practice. The rest require theoretical investigation and much research. For example, compact objects can cause changes in the brightness of gamma-ray bursts when they pass near the line of sight due to the gravitational lensing effect. Another way to detect primary black holes is by observing ripples on the surface of stars. If a black hole were to pass through a star, its density would cause observable oscillations. In the near future, scientists will actively test another theory, that tiny primary black holes have long since evaporated, but if a fourth spatial dimension existed, as string theory predicts, it would affect how gravity behaves on small scales, significantly slowing down evaporation. There are still several thousand black holes left. In order to test this theory, scientists will use the Fermi Gamma Ray Space Telescope. Perhaps they will be able to kill two birds with one stone and discover both primary black holes and take a huge step towards proving string theory. Meanwhile, Michael Brown and Konstantin Batygin have a similar situation with the ninth planet in the solar system. For now, they only have mathematical calculations at their disposal. These calculations were based on the study of the peculiarities of Sedna's movement, and then Brown and Batygin took 6 randomly selected, most distant objects from the Kuiper belt and studied their indicators. Not just based on coinciding parameters, they showed that there is a cosmic body with a mass larger than Neptune and a diameter 24 times that of Earth, which influences these celestial bodies. The percentage of coincidence is so high that scientists do not consider the possibility of a random combination of numbers. These 6 objects have very elongated orbits and are twisted in such a way that they become perpendicular to the solar system disk. As evidence that it is not actually a planet, there are peculiarities in the distortion of light passing through the area of its presumed location. It may be the size of a football, while its mass exceeds that of the Earth by 10 times. Nevertheless, both theories, no matter how well they are built, remain only on paper for now. The most irrefutable evidence of the existence of a primary black hole or planet may 9th be a photograph from a telescope. However, optimism is added by the fact that once upon a time, the existence of Neptune was also only on paper, and this was initially proven only mathematically. One of the greatest and perhaps most important scientific achievements of the last century was the discovery of the expansion of the universe. Distant galaxies are moving away from us and from each other faster than those closer to us, and it seems as if the fabric of space itself is stretching on the largest scales. The density of matter and energy in the universe is decreasing billions of years and shows no sign of stopping. If you look far enough, you can see galaxies moving away so quickly that even if a spacecraft were sent to them today at the speed of light, it would still not be able to catch them. But all of this is hard to imagine. As you may already know, in the distant future, our Milky Way and the Andromeda Galaxy will collide with each other and form a single galaxy called Milkomeda. This raises the question, if the universe is expanding, why are galaxies colliding? This is one of the most common questions in the comments under our videos. We have answered it briefly before and promised to make a separate full video dedicated to this topic, and now the time has come. When Newton first thought about the universe, he imagined space as a grid, an absolute fixed entity filled with masses that attract each other gravitationally. But then came Einstein, who realized that this imaginary grid was not fixed, but rather a fabric that was curved, distorted, and changing over time due to the presence of matter and energy. Moreover, it is matter and energy that determine its curvature. But if there were only a set of different masses in spacetime, they would inevitably collide and form a black hole. Einstein did not like this idea, so he added a correction in the form of a cosmological constant. Einstein did not like this idea, so he added an amendment in the form of a cosmological constant. If this additional term exists in the equation, it introduces additional energy permeating empty space that can repel all of the masses and keep the universe stationary, preventing gravitational collapse. Einstein allowed the universe to exist in an almost stationary state, that is, static and eternal. The idea of a static universe appealed to scientists, but not all. Russian physicist Alexander Friedmann showed that if you don't add this cosmological constant and instead fill the universe with energy, matter, radiation, dust, etc., then there exist 2 classes of solutions, one for a contracting universe and the other for an expanding universe. Mathematics gives us a possible solution, but we need to look at the physical universe to know which one describes it. This happened in the 1920s, thanks to the work of Edwin Hubble, one of the most influential cosmologists of the last century. Hubble was the first to discover that you can measure the characteristics of individual stars in other galaxies and determine the distance to them by combining these measurements with the work of astronomer Vesto Slipher, who showed that there is a shift in the atomic spectrum of these objects. He obtained an amazing result: either the theory of relativity is incorrect, and we are at the center of the universe, and everything symmetrically moves away from us, or the theory of relativity is correct, Friedman is right, and the farther away a galaxy is from us, the faster, on average, it is moving away from us. The theory of an expanding universe moved from a simple idea to a leading description of the universe. The expansion of the universe is a very complex and difficult process to understand, filled with various physical and mathematical formulas. But to understand the essence, let's simplify everything as much as possible and make an easy analogy by comparing the universe to a balloon. Perhaps this is not the best example, but there is no other at hand. First, we will place marks on different parts of the slightly inflated balloon. Then, as we inflate it further, the balloon increases in size and the distance between all the marks increases. Notice that the location of the marks does not change, only the surface of the balloon. If we imagine ourselves looking at the situation from the perspective of one of the marks, we see that all the other marks move away from it. This is how the principle of the expansion of the universe works. Each galaxy is like a mark, and the surface of the air balloon represents the universe. However, the expansion works in a strange way that contradicts common sense. It appears as though the fabric of spacetime is stretching and all objects within it are being pulled apart. The further apart two objects are, the more they are stretched, and the faster they move away from each other. If the universe were filled with evenly distributed matter, it would simply stop expanding and become less dense, with each part moving away from the rest over time. So why do galaxies collide? This is because the universe is hierarchically structured. Galaxies that are close together form clusters, which in turn form superclusters. The expansion of the universe occurs uniformly and acts on a large scale within a cluster of galaxies, which are connected by gravitational attraction. In addition, they are relatively close to each other at a distance of about a couple of 100,000 light-years, so such objects can come closer or move away independently of the overall expansion of the universe. Because of this, galaxy collisions occur. Now, let's add another question to this same topic, which sounds something like this. If the universe is expanding, why is the distance between planets in our solar system not changing? In such a case, the Earth should be moving away from the Sun, but this is not happening. The universe is not perfectly uniform. It has regions of increased density such as planets, stars, galaxies, and clusters of galaxies, and regions of decreased density such as huge cosmic voids where there are virtually no massive objects. This is due to other physical phenomena in addition to the expansion of the universe, such as electromagnetism and nuclear forces on small scales comparable to asteroids or smaller, while gravity dominates on larger scales such as planets and galaxies. The main battle takes place between the expansion of the universe and gravitational attraction of all matter within it. At the largest scales, expansion wins, and the most distant galaxies are moving away from us so quickly that we will never be able to send any signals to them, not even at the speed of light. Superclusters of the universe, long filamentary structures along which galaxies are aligned, stretching for billions of light years, are also being stretched and pulled apart by the expansion of the universe. They will disappear in relatively short periods of time, and even the nearest galaxy clusters, including the one located just 50 million light-years away from us, will not pull us towards them despite their gravitational attraction being more than 1,000 times stronger than our own. On small scales, gravity will win, while on large scales, expansion will win, and the Virgo cluster will remain gravitationally bound.